This is the intro video for Lab 10 of the Apsc 1299 labs. This is for the final project. During the project, your lab instructor may or may not continue to grade your logbooks, but they will keep checking them regardless. This is so we can keep abreast of how your group is doing, but it's also to help save you from yourself, because there's a month and a half between when the project starts and when the presentation happens. Are you going to remember the nuances of what you did on the first day 6 weeks later? Probably not, so it's in everyone's best interest if we make sure that you keep taking good notes. Your lab instructor may allow you, however, to maintain one book for the whole group rather than 3 separate logbooks. You will be required to turn in all versions of your code, including early versions, when you turn in your report. So you need to make a habit of saving incremental versions of the code regularly as you go along. It'll be required. Also, it's just good practice, because if you break the functionality of the piece of code you're working on, it becomes very easy to revert back to an earlier version if you've been saving regularly, rather than just overwriting what you have. As I mentioned a few weeks ago, there is this online resource, github.com, that will help you keep track of older versions of your code. So this is something you and your group members might want to investigate. Once you've started the project, you can turn in your toolkit. You won't need it anymore, and it saves you having to do it later. Your group will need a Picket 2 to work with the robot. If you don't have one, one will be given to you. The robots can be taken home during the project, but you and your group members need to be in agreement about who gets it at what time. So no one in the group should ever be confused about where the robot is right now. You should be at least in that much communication with each other. You can also store the robots in the lab, and we do recommend that you use the lab room as a safe pickup location if you need to trade off the robot from one group member to the other and your schedules don't quite overlap well. Just leave it in the lab room and have the next person pick it up there. And speaking of communication, I'd like to talk a little bit about interpersonal communication. You are engineers, and the simplest description of what you do is you solve problems. So when you're working in a group, people problems are just one of the things you have to deal with. So if you find that there's some friction between group members, don't get mad, just think of it as part of your job. You solve problems, including people problems. So talk to the group member or group members, discuss what's going on, try and work out a solution that everybody's happy with. One common issue is that someone is either not doing enough for the project or they're doing too much and not letting other group members take ownership of the project. So if you're having these sorts of issues or any sort of issues, talk it out, see if you can work it out amongst yourselves, and if it's really getting bad, please do talk to your course instructor and your lab instructor. We do want to help you have a good experience with the project. Now, the reason why we assign you one robot and don't let you switch to a different robot is that every one of the robots has its own little idiosyncrasies, and it's important that you learn to code for the quirks that your robot actually has. So the solutions you find that work well with your robot may not work well on a different one, which is why it's important that you work with the same robot consistently. Now, for testing purposes in the lab room, you can make tracks using the white cardboard that we've provided and electrical tape for the black lines. There's also some older student-made tracks left over from previous years that might be useful to you. Please only test the robots on tracks that have been placed on the floor. This is especially true in Surrey, or inside the wooden frames on the desks that have been placed out in Richmond. That's just to make it impossible for the robot to zoom off the side of the desk. Also, please note that the competition track is going to be printed on paper, so rather than being electrical tape, so it may not be as dark as the electrical tape. However, on race day, you'll be given a chance to test your robot's sensor response on the track before the race, and then you can adjust your threshold value if you need to. In the lab manual, the project objectives tell you a little bit about what to expect in the competition, and I'm going to expand on that now. The robot has to navigate an obstacle course that's a printed black line on a white background, and you will not get to see the track before race day. Your robot will get 2 tries on the track, and maybe 3 if we have enough time, and you are allowed to tweak your code in between runs to try to get a better performance out of the robot. There's always going to be an obstacle course track, also called the technical track, and some years we also have a speed track. You'll have to ask your course instructor whether or not we'll have a speed track this year. The speed track, if there is one, consists of a relatively simple track, and the fastest robot through it wins. The obstacle course or technical track is a set of increasingly difficult challenges that your robot has to navigate. Your grade will be based on completeness, that is, how far along in the obstacle course your robot got. We do record the time that it takes your robot to complete the technical track, but that time is only used as a tiebreaker in the event that there's more than one team that completes the entire course without any touches. What do I mean by touches? You could touch your robot up to 10 times, basically to rescue it if it fails to complete some obstacle. So if your robot doesn't make it through one challenge, you can grab the robot, move it back before that challenge, and retry that obstacle. There is a grading penalty associated with each touch, however. It's usually about 3%. If your robot can't complete a certain obstacle after 3 tries, then you're allowed to move it forward past that obstacle and let it attempt to complete the rest of the track. If you'd like to see previous year's competitions, go to YouTube and type in APSC 1299 Quantlen, and that should bring up several videos where you can watch a competition from a previous year. So now I'm going to go over some challenges you're likely to see on the technical track. By the way, this handout should be posted on the website. So the first challenge to be aware of is tight curves, where the radius can be as little as 7 centimeters. Keep in mind that the wheelbase of the robots is only 10 centimeters, so a radius of 7 centimeters is not quite spinning on one wheel, but is getting pretty close. It is a very tight curve. Scrolling down, the next one to be aware of is turns, right and left. So it might be a large angle turn, a right angle turn, or a small angle turn. If it is a small angle turn, the minimum is 30 degrees. There's also crossovers. So in a crossover, your robot is expected to go straight. So it would come along here from the bottom, for example, and when it hits the crossover, it just ignores that and keeps going straight. Same thing here with this acute intersection, is if it was coming in here from the bottom, it would just keep going straight and not veer off, for example, to one of the other lines. One thing to note is that this acute intersection and the small angle turn look exactly the same when the robot's coming into them. You have to get to this point, just past the intersection or just past the turn, before the robot can determine what it should do. So you might consider coding for both of these cases at the same time. There's actually quite a few situations like that, where the robot would see a certain pattern of inputs, but it would have to wait a certain amount of time to see what comes next before it can make a decision about what to do. So you should identify those sorts of situations and maybe try and code for those things all at the same time when you realize that there's some overlap. Scrolling down again, your robot should be able to handle a gap of up to 8 centimeters, meaning, for example, if it's coming up here from the bottom, if it reaches a point where it's got no inputs, that is, it's found a gap on the line, it should keep going for at least 8 centimeters until it finds the line again, and then it would continue following it. In this second case, again, if you were coming up from the bottom, it would reach a point where it has no inputs, and it should keep going for up to 8 centimeters trying to find the line. And when it hits this input, it should then realize that it needs to turn and follow this line. This third case is actually the trickiest one. If you're coming in along the diagonal, it runs out of inputs, and then the first sensor to get triggered is its leftmost sensor, even though the robot needs to turn right at this point. So as I said, that's the tricky one to code for. Scrolling down again. Your robot has to be able to handle nearby trails, that is, when another track comes close enough to the track that the robot's on to trigger its outside sensor. You don't want the robot to get confused, jump off the track, and start following the other line. So they note here that the trails can be as little as 2.5 centimeters apart. Recall that the robot is only 10 centimeters wide, so this definitely would trigger its outside sensor. So scrolling down again. So your robot should be programmed to handle gaps of up to 8 centimeters. But when the gap is larger than that, it should treat it as a dead end, turn around, and head back the way it came. At the very end of the track, we have what's called a landing pad. It's a black square, slightly larger than the robot's footprint, and to get full marks on the technical track, your robot has to stop on that black pad. Now, having told you about all of these challenges, I will note that one of the trickiest things about the technical track is that you're often hitting these challenges one after the other after the other. So for example, if you're coming around a tight curve and then your robot hits an acute turn, it may not have straightened itself out entirely, and that may affect how well it navigates the acute turn. So generally it's a good idea to start simple and add complexity later, so I would recommend making sure that your robot can navigate all of these challenges individually and then start worrying about how it will handle them when it hits a challenge a little bit off center. Another thing to be aware of is that battery life can affect how your robot handles. So for example, really fresh batteries can cause your robot to behave really jittery, and one thing that's always a problem is that as your batteries run out, the motors start to run more slowly. However, the chip's still running at the same pace, so that means that your delays and your timers are still measuring out the same amount of time, but your robot's not going as far during that period of time as it used to. So that affects how well it deals with gaps and dead ends. Unfortunately, dealing with the quirky things that your robot does, depending on how fresh its batteries are, is just part of the project. So do your best with that and just be aware that it does affect things. Now every week your group should come up with a task list for the lab period. That means a list of tasks that you intend to complete during that lab period. So there's an example down here in your lab manual. So your task list would be a short description of the task, an estimated time to complete it, who the task leader is. That's not necessarily who does all the work. You can work as a group, but the person who's in charge of that task. And then a self-evaluation, which would be left blank to begin with. You would show your task list to the lab instructor at the beginning of the lab period, and then you'd start working. And at the end of the lab period, you fill in your self-evaluation. So for example, if you only got 50% of task 2 finished, then you'd fill in 50% here, saying you only got half of it done. Then you show the task list to your lab instructor again. Some lab instructors will assign a grade to you based on this. However, some of them also won't. Then, if possible, before you leave the lab room, you and your group should discuss what you plan to do over the course of the next week. It would be ideal if you made up another task list for the week, but nobody's going to be looking at that one, so it's really up to your group. What's important is that everybody in the group knows what they should be working on over the course of the next week. It's good to split up the work, but maybe you want to also talk a little bit about how to reduce code conflicts. So maybe you want to agree ahead of time what sort of variable names to use. Things like that. So we have a diagnostic program that allows you to test whether or not your motors on your robot are functioning properly. So this is our lab, and over here we've got the windows and the side counter. And if you go right up to this computer, this is the very front computer beside the sink, this is where the diagnostic program is running. And on the wall behind it are the instructions, but I'm going to go through all of those with you. So the first thing you're going to need to do is to program the diagnostic program onto the robot. So that should be fairly familiar. Plug in your Picket 2, plug it into the robot, and then turn on the brain board. Then you open MPLab, and the robot diagnostic program should already be loaded up as the main project. If it isn't, then you can go through the instructions on the wall to load it up, but assuming that it has been already loaded as the main project, you can just build and program this program onto your robot. Now you unplug the Picket, and you need to plug in this cord that says Robot Diagnostic. It should already be plugged into the back of the computer, and you need to get the white dot on the cable lined up with the white stripe on this little connector on the top of your robot. You don't need MPLab anymore, so you can shut that down. And next you're going to open up a program called PuTTY. So I've opened that up here. The settings you need are listed in the instructions on the wall, but I'm going to go through all of these with you. So first, click on Session. That's probably the default that you're already on. And you want to change this radio button down here to Serial. Now that will change the serial line to COM1, which is what you want. The speed will be set incorrectly, so you want to change that to 115200. Next, you come down here and you click Serial. Most of these will have filled in automatically and be correct, but you do want to double check with the instructions on the wall. The very last setting down here, flow control, probably will need to be changed to none. And then you click Open. That brings up this screen, which doesn't look too interesting, so to make it look interesting, click Enter. And that should give you this text-based menu. If Enter doesn't work, try clicking U for up. That's how you navigate through the menus. Now there's two menus that you can access here. There's M, which gives you the motor menu, which allows you to test your motors on your robot, and S, which allows you to test the sensors on your robot. So I'll click M first, and I get this sub-menu, and I can click L for the left motor, R for the right motor, and B for brake all, so putting on the brakes. So I'm going to click R to begin with. That allows me to set the speed of my right motor. So I'm going to set it to fast by clicking F. And you need to turn on your motor switch for this to work. So now my right motor is moving at fast speed, and if I go up by clicking U, I can now click L to access my left motor, and I can set its speed to medium by clicking M, for example. And so now my left motor is moving at medium speed, and my right motor is moving at fast speed. I can click U to go up one level, and then B for brake all to put on the brakes, and now both motors have stopped. So now let me show you what that looks like. So again, I'll go to the right motor and then go fast speed. And now you can see that my right motor is going at fast. And I can go up a level and then select the left motor and say go at medium speed. And now it's going at medium speed and this one's going at fast speed. And again, I'll click U to go up a menu and then B to stop them. So break all is the B. So this is useful if you're finding that your robot's not responding. It could be your code is screwed up, or it could be that something's wrong with the robot. So you can test it with this diagnostic program and see whether the motors are working correctly. If they don't seem to be, take it to the technician to get fixed, and if the robot checks out fine with the diagnostic, that means the problem is in your code somewhere. So now I'm going to turn off my motor switch, and I'm going to show you how you can check on your sensors. So first I click U to go up to the main menu. And now I'm going to click S to go into the sensor menu. Now as you can see in this sub-menu, I can click 1, 2, 3, 4, and 5 to read the sensors directly. So for example, I can take my robot and put it on top of a black line so that only one sensor is being triggered. And I can click 1, and it gives me the raw reading for sensor 1, 111. I click 2, it gives me a reading for sensor 2. I click 3, that one's much bigger, 837, because that's the sensor that's on top of the black line right now. I click 4, it's much smaller because again that sensor's not on the black line. I click 5 to get sensor 5's reading. So I can go and look at all of what my sensors are reading in real time, depending on whether they're sitting on black or white. Now up here in this menu, note that there's two other options. There's T, which allows you to set the threshold value for your robot, and A, which is an automatic threshold setup program, where the program decides what it thinks the ideal threshold for your robot should be. So first let me click T, and you see that it tells me the old value for the threshold was 512, and I can now set a new value for the threshold. So I'll type in 500, hit enter, and it says up here that the new threshold value has been set to 500. I'll press T again just to test that, and it says yes, the old value is 500, go ahead and set a new one. So I'll move it back to 512. And now let's try out this automatic threshold setup. So how this works is that you're going to take your robot, you'll click A to start the program, and then you'll slide your robot from left to right with the nose pointing away from you across a black line, triggering each sensor in turn. And when you're done, the program's going to determine what it thinks the best threshold for the robot is. So let me do that now. I press A to start the program going, and then I slide my robot from left to right with its nose pointed away from me across a black line. And when I'm done, the program decides, okay, 324 is what I think the ideal threshold for this robot is. Now you may want to change your threshold to a different value anyway, depending on how your robot handles, but it's useful to know what the program thinks the ideal value should be. So right now I've got the threshold value set very high. That means my robot's not very sensitive. And the problem with that, if you watch the LEDs, is that it is possible for me to have the robot over top of a line with no LEDs lit. So it's not detecting anything right now. So I want it to be more sensitive. That means I need to lower the threshold to a smaller number. So now let me set the threshold to a value that's too small. So now when I slide it over top of the line, you'll see that it's possible for me to get two lights on at the same time. You don't want that either. It's a good second best. The worst case is when the robot can't detect the line at all, even when it's over top of the line. Having two of the sensors detected at the same time is better, although still not ideal. What we would ideally like is for only one sensor to be triggered by the line. So now I'll use that automatic threshold setup program. So I move this guy over here, and I type A, and now the program's ready, and I just slide the robot across the line in this direction, so from the left to the right. And after I've done that, the program has said, okay, now my threshold value is 471. So it has selected what it thinks is a good threshold value. And now, when I move my robot over top of the line, I should see pretty close to one LED being on at a time. So I shouldn't see any gaps where the LED is not lit, and potentially you might see a case where two of them are lit, but hopefully not for very long.